The topic of the present lecture is getting out how to study of designs and how to improve a design to get a better design. This is related to the topic of database decomposition in general, and we will look at it as the topic on improving a design. A design of a database will be a set of attributes, relation schema, a set of schema, relations, a set of functional dependencies, and the other constraints. Now, based on these, we will have to see whether this design is a good design or not. So, what do we mean by a good design? We are given a database and we are given a set of functional dependencies, and we would analyze this relational schema or relation and the set of functional dependencies and the other constraints and see whether it is a good design in terms of what we have seen till now in the initial design. The initial design is adequate. It is adequate in the sense that it properly models whatever information I require to model. I have got all the constraints which I need to check, and I have got all the information which I have to provide. Similar to this is the design of algorithms. You can design a program or an algorithm which works, which for the given input works correctly for the given output. But to consider whether it is a good algorithm, the first thing that comes into the picture is that of efficiency. And here again also we have to look into the question of efficiency related to the execution time of whatever queries that come up and whatever updations, deletions, insertions that come up in a database design. And there are various issues relating to a good design. And there are various steps in generating a good design. First, we have the concept of decomposition. Then we have the question of query optimization. And finally, we have decomposition tries to ensure that the updations, the insertion, deletion and updations to a database, and the checking of functional dependencies, the checking of all the integrity constraints are done very quickly. They are done efficiently. That is the objective of decomposition. Query optimization tries to ensure that each query is evaluated fast. And all the query optimization and the quick checking of functional dependencies are all dependent on efficient handling and implementation of files. That is how the database tables are implemented at the low level. So, we will study the high level techniques first, and then we will study the low level technique. So, first we will look into the question of database decomposition. Let us see a very simple example of a database which has been designed. It is a supplied by relationship, slightly different from the one which we had taken out before. It contains supplier name, supplier address, item and price. And we have got two functional dependencies. Supplier name gives supplier address, and supplier name and item together gives price. So, this means that a supplier name must have the same address, two supplier name, two tuples which have got the same supplier name must have the same address, and two tuples which have the same supplier name and item must have the same price. So, looking at it quickly, supplier name and item gives you the primary key or the candidate key for this relation. Now, let us look at it from the point of checking up the functional dependencies in terms of insertion, deletion. Let us look at it in terms of the space which is required to store these. Now, a supplier may supply thousands of items. Whenever you have a table which has got a supplier supplying one item, say sugar, then another item salt and another item, each case you will put in the supplier address. So, the first thing which comes here is the issue of redundancy. And this issue of redundancy grabs up a lot of space. But space is not the first and foremost criteria here. A lot of problems will automatically come up whenever there is redundant information like this. The first thing that will come up is the checking of functional dependencies. Whenever a new supplier supplies a particular item, the functional dependency supplier name to supplier address will be checked. Not only will that supplier address be there unnecessarily, that supplier address will have to be checked. So, that is the first problem that will come up. The second and more complex problem that will come up is if the supplier address is changed. He just shifts and puts in a different address. From 3 Mango Lane, he puts in 2 Chaurangi Avenue or something like that. Now, in order to protect this functional dependency, all tuples wherever the items are supplied, in each and every place, this address will have to be changed. Because if that is not changed, this functional dependency will be violated. So, that redundancy puts in a lot of extra effort and may lead to, this redundancy actually leads to difficulties in insertion, What is the difficulty in insertion here? Whenever it inserts a new item here for a particular item, then this address has to be changed, this functional dependency has to be checked. And all the places where this name and address goes, it starts checking. The deletion one is even more complex. The point is that if I delete this tuple and I start deleting tuples, and if a supplier currently supplies no item, I may lose the supplier name and address. If I have only this as my relational schema, then I may lose supply name and address, which I may not want to lose. So if I don't want to lose that, I will put in null values. That is, whenever I find out, I will put in an assertion or a trigger or something like that, which says that now if I delete, after deletion, on deletion of an item, if I see that this supplier name gets deleted from the old table, then I have to insert a new tuple which has got only name and address and null fields here. And if I put in this null concept, then I lead to difficulties in insertion. Whenever I insert a new tuple, I have to remove this null tuple. Or if I keep that null tuple, then I'll have to be careful when I check the functional dependency supplier name, item and price. But I will put supplier name, item and null and null. And I will unnecessarily not like to have many null tuples out there. And so a lot of problems will come up just based on having this redundant information. And since updation is a combination of insertion and deletion, all problems related to insertion and deletion will automatically come up when we do updation. So what is the solution? The suggested solution is break it up. The suggested solution The next question is, how do you break it up? If we have to break up this into more than one relation, how do I break it up? The most natural way to break it up here in this particular problem, one way to break it up is like this. With the same functional dependencies, S name to S address and S name item to price. I will check this functional dependency here and I will check this here. Now I do not have all the problems which I envisaged previously, because for a supplier the address is only stored once, and if I change it here, it is sufficient to change it here. And whenever items are added or deleted, even if he supplies no item, there is no problem for me. Whenever I update an item, I need not modify this address. I need not repeatedly write addresses. Only the supplier name is repeated in two of these places. So I save myself from a lot of difficulties here, and this functional dependency is very efficiently checked. It is not required to be checked in any operation that goes on here. Only this functional dependency will be checked here, this functional dependency will be checked here. So that looks like a good design. At least compared to this is a much better design. We had this problem. We had supply name, address, item, price. Suppose we broke it up into supply name and address and price. would this be a valid decomposition? Intuitively it looks very odd. Intuitively it looks very odd that supply name, this supply name supplies this item, and this is the address of the supplier, and this is the price. The difficulty will be that if this supplier item supplies this item at a price say 50, how will I know that? How will I know that supplier name XYZ supplies an item sugar at price rupees 50? What is the price at which supplier name XYZ supplies this item? I will not be able to know. So, when I decompose my original one, I must not lose my original adequacy information. Whatever I could get from that one, I must not be able to lose. I must be able to obtain. Is that obtainable here? Is whatever information could be obtained here, is it possible to obtain it from here? How? If the answer is yes, in this particular case it is yes, and in this particular case it is no. In this one, when I decompose like this, it is yes, and in this one, when I decompose like this, it is no. What is the inherent reason behind this? When will you say a decomposition is correct? That is, it does not lose information. We will say, look at this one. You can always reconstruct this one from the original one can be recomposed, reobtained by doing a natural join of the decomposed functional dependencies. And in this particular case, you do a natural join of these two, you will get back this. You are necessarily going to get back this one from a natural join of these two. But because there is no common item, and since there is no common item, it is going to become a Cartesian product. It is going to give you a much larger set than S by. So here, if you wanted to find out, here you can find out that give me all the items which are supplied by a supplier who has address shop number 35 IIT Market. This you can ask this same question here. Give me the items which are supplied by a supplier whose address is shop number 24 IIT Market. How will I get it from here? I will have to do a natural join and get it from here. But if I try doing this, I will get all wrong answers. Here I have taken no common attribute. Let us take one common attribute. Will this be okay? I have got only two functional dependencies, S name to S address, and I have got S name item gives price. If I decompose into these two, will S by equal to P1 natural join P2? No, it will not be equal to P1 natural join P2. because item does not, it is just because this does not hold. You will have some extra information. You do a natural join of these two, and then you break it up into these two, you will see you get some extra information. So such decompositions are not allowed, they are not valid, and we will not have such decompositions. Such decompositions are called lossy decompositions, whereas a decomposition of this type is called a lossless decomposition. So whenever we look at insertion, deletion and updation difficulties, we would also, whenever these situations arise, we would like to have a decomposition. But we would also like to have a decomposition which is lossless, because the other one is not only lossy, it is meaningless. This decomposition issue came up because of these difficulties. Plus, please remember that decomposition always does not lead to efficiency in every aspect. It leads to efficiency in checking of functional dependencies in this case. But I suppose my query, a very common query was, get me the item supplied by a supplier whose address is something. Then this decomposition will be inefficient in terms of time, because every time I require to solve that query, I will have to do a natural join and then get that query. The natural join is obviously much more complex than just getting a query from a table. So when we look at the difficulties of redundancy, this decomposition comes up, but it has to be taken with a pinch of salt, and it has to be always remembered that when we come back to efficiency in terms of time, there are other issues, and the issues are related to those queries which may come. For the time being, we will not take up that question. For the time being, we will look at decomposition from our redundancy point of view only. But we will try and address that issue a little later. First, let us understand what are the types of decomposition that we can have. In order to do that, we will pick up the second example. This is a bank loan. A customer in a branch, a loan number and an amount. And I have got this, that whenever loan number is same, the amount must be same, which is quite obvious. Customer name same, amount must be same, and customer name same, loan number must be same. Which means that a customer can take only one loan. Customer, loan number, amount. So customer amount, this is redundant actually. This one is redundant. So how will I break this one up now? Will this be okay? Is this a lossless decomposition? Note here that loan number is not a primary key in this whole thing, but this is still a lossless decomposition. Loan number is not a primary key here, but this is still a lossless decomposition. And when I break it up, I will check this one here and I will check this one here. But by chance, let us say I had the same one this is a loan, C name, suppose I am just putting in a supposition, not this may not be absolutely realistic just now. So, I have got C name to loan number, I have got loan number to amount, and finally, suppose I have got amount to this means that a particular branch can give only if the 5 lakh rupee loan you can get only from that branch, 10 lakh rupee loan you can get from this branch, 20 lakh rupee loan you can get from another branch. That is what it means. Now, how will I decompose? I can decompose how? What will I do? Will I put L1 loan number amount, L2 C name, BR name, loan number? This is the previous one which we had done. This is fine. Loan number amount, this is lossless. This is lossless, there is no problem here. This is lossless. But can you identify what is the difficulty here? What is the problem with this? This functional dependency can be checked here. This functional dependency can be checked here. But to check this functional dependency, how will I check this functional dependency? To check this functional dependency, I will have to do a natural join of these two and check the functional dependency. Not that it cannot be checked. This is a lossless decomposition. In order to check this functional dependency, I will do a natural join of these two. So, I will do L1, natural join L2, and then check this functional dependency. So, you can well imagine the amount of computational effort that will go in checking this functional dependency. So, we come to another desired property. This is a desired property. This is not a property like lossless and lossy which will make the decomposition incorrect, but this is a desirable property which says that after you decompose, you should not be you should be able to have a new set of functional dependencies such that covers the original set of functional dependencies, and you can check it only on the individual decomposed relations. You need not do a natural join to check it. That is called dependency preservation. And in this one, dependencies are not preserved. So, looking at the question of decomposition and looking at what makes a good design in terms of decomposition, in terms of how we can break up a relation, what are the properties? The first and the primary property was reduction of redundancy. And in order to reduce redundancy, we started to carefully decompose the relations. It has to be done very carefully, of which when you decompose, the first is a very necessary criteria. It is the lossless join. Otherwise, information will be lost. Some arbitrary extra information will actually come. And the second is a desired property of dependency preservation, because if you don't have dependency preservation, you will see that it will become computationally very inefficient in terms of checking the functional dependencies. So now, how to get about designs which are lossless join, how to decompose to lossless join and dependency preserving relations, we will see later on. Therefore, we will stop today with the notion of what are the properties of a desired good decomposed database scheme.